So let's take a look at finding volumes, specifically looking at the disk and washer methods. Now starting off with the disk method, let's say we have a region here that's bounded by these curves and we want to rotate that region around the x-axis. Well, if I draw another graph depicting what that region or what that solid would look like when we rotate that region around the x-axis, we get a sort of cone-like shape. And in order to find the volume of this cone, we have to use what's known as the disk method. So the formula for the disk method, the volume equals pi times the integral from a to b of r of x squared times dx. Now a and b are just going to be our bounds of integration. So obviously if we look at this region here, a is going to be the lower bound and then b is going to be the upper bound, and then r of x is going to be representing the radius. So the radius of the solid is going to be the distance from the axis of rotation to the outer curve. So in this case, if I go ahead and erase the blue shaded region here, the axis of rotation is obviously the x-axis, and the distance from the x-axis to the outer curve is just going to be the curve itself, because whatever the y value of the curve is, that's going to be the radius or the distance between the axis of rotation and the curve. So for example, if this curve represented y equals the square root of x, at the specific x value of 2, let's say at that point we have the x value of 2, then this y value would be the square root of 2. And the square root of 2 is going to be the radius or the distance from the horizontal or x-axis to the curve. Now let's say you're trying to rotate a region about the y-axis instead of the x-axis. Then the volume formula you will use is volume equals pi times the integral from c to d, and those just represent y bounds of r of y squared times dy. So realize that when we're rotating around a horizontal axis like the x-axis, we put everything in terms of x, and when we're rotating around a vertical axis like the y-axis, then we put everything in terms of y, and that's the only change we have to make. So now moving on to the washer method. Let's say we have the same region as before, but this time we're going to rotate this region around the y-axis. Now the main indicator for when you should use washer method is if the solid generated by rotating the region around a certain axis has a hole in it, then we use the washer method. So obviously between the region and the axis of rotation, there is space here that separates the axis and the region. And because there is space, when we rotate that region around the y-axis, there's going to be a hole in the object that we create. So because there is a hole, we have to use the washer method. Now the formula for the washer method is going to be volume equals pi times the integral from a to b of the outer curve squared. So the outer curve is just represented as capital R of x squared minus the inner curve, so the lowercase r of x squared times dx. And that's if we're rotating once again around a horizontal axis. But in this example that we did here, we're rotating around a vertical axis, so we just have to put everything in terms of y, where the volume equals pi times the integral from c to d of capital R of y squared minus lowercase r of y squared times dy. Now once again, capital R represents the outer curve. So how do we find the outer curve? Well, we start from the axis of rotation, which in this case is the y-axis, and we go out to the outermost curve. In this case, the outermost curve is that vertical line, so that is going to represent capital R of y in that case. Now lowercase r of y represents the inner curve, and the inner curve, in order to find that, we still start from the axis of rotation, and this time we go to the inner curve. In this case, the inner curve is going to be, as we mentioned before, y equals the square root of x. So for these next set of problems, we have to find the volume of the solid by rotating the region bounded by the given curves about the specified line. So for number 1, we have y equals x squared, x equals 1, and y equals 0, and we have to rotate the region about the x-axis. So the very first thing we have to do is go ahead and draw these curves. So I go ahead and graph out y equals x squared. That's going to look something like this. We have x equals 1. Let's just say that's around here. And then we have y equals 0, which is basically the x-axis. So that's going to be y equals 0. Now the area or the region being bounded by those curves is exactly right here. And we want to rotate that region about the x-axis. So rotate it about the x-axis. Now I'm going to redraw this graph and just zoom in on the first quadrant, because that's where the region is at. So we have y equals x squared, which is right here. We have x equals 1. and then we have y equals 0, which is the x-axis. So we're looking at this region here, and once again we're going to rotate that region about the x-axis. Now realize that there is no space separating the axis of rotation and the region, so we can use the disk method because there's not going to be any hole when we rotate this region about the x-axis. And to show you a visual example, if I were to actually rotate this about the x-axis, we would get something like this. So no hole in the object, just a solid object. Now because we are rotating about the x-axis, we have to put everything in terms of x. So we're going to use the formula where the volume equals pi times the integral from a to b of r of x squared times dx. Now if I were to rewrite the formula filling in the information, the volume is going to equal pi times the integral. Now a and b are just our x bounds. So our x bounds range from 0 to the line x equals 1. So we can say it ranges from 0 to 1, so the integral is from 0 to 1 of our radius squared. So in order to find our radius, we need to find the distance between the axis of rotation and the curve. So if I were to erase this shaded region here and fill in some of those lines, the distance between the axis of rotation, which is the x-axis, and the outermost curve is just going to be the curve itself. That's going to be y equals x squared. Now once again we have to put everything in terms of x, so the radius in terms of x is going to be x squared, and then we have the radius squared, so x squared squared times dx. So now we can just simplify and then evaluate the integral. Now rewriting the integral, we have pi times the integral from 0 to 1 of x to the 4th times dx. So now we have pi as a constant times the integral of x to the 4th. We can just use the power rule and we'll get x to the 5th over 5. And then we can evaluate from the x bounds of 0 to 1. So we have pi, that's just a constant. I can leave it outside when I'm evaluating. Times, when I plug in 1 for x, we get 1 to the 5th over 5, which is 1/5. Minus, when I plug in 0 for x, we just get 0. So that'll give us our final answer of 1/5 pi, or pi over 5. Now for number 2, we have y equals x squared, and there's a restriction on that function where the x values range from 0 to 2. We have the line y equals 4, we have the line x equals 0, and we're going to rotate this region about the y-axis. So let's start by graphing these curves. Now if I go ahead and graph y equals x squared, it's going to look something like this. Now once again, the restriction is that the x values can only range from 0 to 2. So let's go ahead and draw y equals x squared with the restriction that the x values go from 0 to 2. So obviously we have 1, 1 right here. We have 2, 4. That's another point. So 1, 2, 3, 4. So I'm going to erase the left half of y equals x squared because once again that is our restriction. Now the next curve is y equals 4. So that's going to be right here. And then we have x equals 0, which is basically the y-axis. And so the region being created here is right here. And we want to rotate that region about the y-axis. So rotate it about the y-axis. Now realize that there is no space between the axis of rotation and the region itself. So we can use the disk method. However, we are rotating around a vertical axis, the y-axis. So we have to put everything in terms of y. So the formula for the disk method, once again, volume equals pi times the integral. Now this is going to be for our y bounds. So where do our y values range from? Well, they range from 0 all the way to 4 for the region. So our bounds are going to be from 0 to 4. And then we have the integral from 0 to 4 of our radius squared. So, and our radius, remember, is in terms of y. So what is the radius? Well, the radius, once again, is the distance from the axis of rotation to the outermost curve that we rotate. And that outermost curve in this case is going to be y equals x squared. However, remember that we are rotating about the y-axis, so we have to put everything in terms of y. So I just need to isolate x and say that x equals plus or minus the square root of y. Now, even though we got x equals plus or minus the square root of y, this curve only represents positive square root of y. Well, negative square root of y is just the reflection across the y-axis. So really, we're only going to use positive square root of y. So our radius is positive square root of y, and remember the radius is squared, so we have positive square root of y squared times dy, because once again we're putting everything in terms of y. So now rewriting the integral, volume equals pi times the integral from 0 to 4. Those are our y bounds of our curve, square root of y squared, which is just y, times dy. Now evaluating this integral, we have pi times the integral of y, which is y squared over 2. and then we can evaluate from the bounds of 0 to 4. Once again, those are our y bounds. Now when I evaluate pi is just a constant, so pi times, when I plug in 4 for y, 4 squared is 16, 16 over 2 is 8, minus when I plug in 0 for y, that's 0, 8 minus 0 is 8, and 8 times pi will give us the final answer of 8 pi, and that's the volume. So now for number 3, we have y equals x squared equals x, and we're going to rotate the region about the x-axis. So if I were to go ahead and graph this, we have y equals x squared, we have y squared equals x. Now the first thing I'm going to do is isolate y so that I can actually graph it. So if y squared equals x, y is going to equal plus or minus the square root of x. So we already know what positive square root of x is. That looks like this. And negative square root of x is just the reflection across the x-axis. So the region being bounded by those two curves is right over here. And we're going to rotate that region about the x-axis. Now realize that there is space in between the axis of rotation and the region. So when we rotate this region, and the solid that we create is going to have a hole in it, so we have to use the washer method. Once again, the formula for the washer method, volume equals pi times the integral from a to b of the outer curve squared minus the inner curve squared times dx. Now because we are rotating around the x-axis or a horizontal axis, we have to put everything in terms of x, so this is the correct formula to use. So volume is going to equal pi times the integral. Now for our a and b, our bounds of integration, they range, obviously the origin is one intersection point, so the bottom bound is going to be 0, and then the top bound here, the other intersection point, in order to find that, I mean we can guess it's 1, but just to double check, we can set both of those equations equal to each other to find what the correct x value is at where they intersect. So I can set x squared equal to, now I'm not going to set it equal to plus or minus the square root of x because this curve only represents positive square root of x. So I'm just going to set it equal to positive square root of x. Now the first thing I'll do is square both sides of the equation. So x to the 4th equals square root of x squared, which is x. And then I can go ahead and subtract over the x. So x to the 4th minus x equals 0. When I factor out an x, we have x times x cubed minus 1 equals 0, and then I can solve for each of those factors. So I'm just going to write down here, if x is equal to 0 and x cubed minus 1 is equal to 0, then x cubed equals 1 and x equals the cube root of 1, which is also 1. So those are our 2 points of intersection. So now that we have verified that the bounds go from 0 to 1. So now we have the outer curve squared, or the outer radius squared, minus the inner radius squared. So in order to find the outer radius, I'm just going to go ahead and erase some of this because we don't need the other half of this curve. Now in order to find the outer radius, I'm actually going to also erase the shaded region. We have to start from the axis of rotation, which is obviously the x-axis, and we go to the outermost curve. Well, in this case, the outermost curve here, or the distance between the axis of rotation and the outermost curve, is just the outer curve, which is y equals not plus or minus square root of x, but just positive square root of x. So our outermost curve, r of x, is square root of x. So we take square root of x squared, and then minus the inner curve squared, or the inner radius squared. Well, the inner radius is the distance from the axis of rotation to the innermost curve, and in this case the distance is just the innermost curve itself, which is y equals x squared. So x squared is going to be the lowercase r of x, so we have x squared squared times dx. Now simplifying the integral, we have pi times the integral from 0 to 1, square root of x squared is x, minus x to the 4th times dx. So now we can just go ahead and evaluate the integral. So we do have pi times the integral of x, which is x squared over 2, and then minus the integral of x to the 4th, which is x to the 5th over 5. And then we can evaluate from the x bounds of 0 to 1. So we have pi times, when I plug in 1 for x, we have 1/2 minus 1 over 5. Minus, when I plug in 0 for x, we have 0 minus 0, which will just end up canceling out. So what we have left is pi times 1/2 minus 1/5. Now I can just go ahead and combine those two fractions. So I can rewrite 1/2 as 5 over 10, and rewrite 1/5 as 2 over 10. 5 over 10 minus 2 over 10 is 3 over 10, so that gives us our final answer of 3 pi over 10. So now for number 4, we have y squared equals x equals 2y, and we're going to rotate the region about the y-axis. So if I were to go ahead and graph this, now y squared equals x, I can isolate y and say y equals plus or minus the square root of x. We've already graphed that in the previous problem. Obviously, positive square root of x looks something like this, and negative square root of x is just the reflection across the x-axis. And then we have x equals 2y. So if I isolate y is then going to equal 1/2 x, or x over 2, which is going to end up looking something like this. So the region bounded by those two curves is right here, and we want to rotate that region about the y-axis. So I'm just going to go ahead and erase the part of the curve that we don't need here, and just focus on the region itself. Now realize that there is space in between the axis of rotation and the region, and because there is space, there's going to be a hole in the solid when we rotate the region about the y-axis, so we have to use the washer method. Now we are rotating about the y-axis, or a vertical axis, so we have to put everything in terms of y. So the formula for the volume is going to equal pi times the integral. Now in this case, our bounds are going to be y bounds. So where do our y bounds range from? Well, we know the bottom bound is at the origin, so it's at 0, and we need to find what that top bound is. Well, in order to find what that top bound is, I can go ahead and set the original two equations equal to each other to find at what y value do both of those curves intersect at. So I set y squared equal to 2y. Now I can actually go ahead and subtract over the 2y. So y squared minus 2y equals 0. I can factor out a y, so y times y minus 2 equals 0. And then I can set both of those factors equal to 0. So y equals 0, obviously that's one of our intersection points. And then we also have y equals 2, which is going to be that other intersection point. So our bounds range from 0 to 2. Now obviously in washer method we have the integral of the outer radius squared minus the inner radius squared. So if I were to clear up some of this here, in order to find the outer radius, the distance from the axis of rotation to the outermost radius is just going to be that outer radius, or the outer curve itself. And that outer curve is going to be x equals 2y. Once again, we have to put everything in terms of y because we're rotating about the y-axis. So it's going to be 2y squared. That's going to be the radius squared, or the outer radius squared. And then minus the inner radius squared. Well, the inner radius is going to be the distance from the axis of rotation to the inner curve. And the inner curve here is x equals y squared. So y squared squared is going to be the radius squared. And then we have dy on the outside. Now simplifying the integral, we have pi times the integral from 0 to 2. 2y squared is 4y squared minus y to the 4th times dy. And then we can go ahead and just evaluate from there. So we have pi times the integral of 4y squared, which is 4 over 3y cubed. And then minus the integral of y to the 4th, that's y to the 5th over 5. And then we can go ahead and evaluate from the y bounds of 0 to 2. So then when we evaluate, we have pi times, when I plug in 2 for y, we have 2 cubed, which is 8. 8 times 4 is 32. So we have 32 over 3. Minus 2 to the 5th, which is 32. 32 over 5. Minus, when I plug in 0 for y, we have 0 cubed times 4 thirds, that's 0. Minus 0 to the 5th over 5, that's also 0. That will end up canceling. So all we have left is pi times 32 over 3 minus 32 over 5. I'm just going to go ahead and use a calculator to find the final answer. And your final answer should be exactly 64 pi over 15. Now for number 5, we have y equals x, y equals the square root of x, and we're going to rotate the region about y equals 1. So the very first thing you should notice is that now we're rotating about something other than just the x or y axis. We're rotating about the line y equals 1. So if we go ahead and graph this, we have y equals the square root of x, which looks something like this. We have y equals 1. That looks something like this. So obviously the region bounded by those two curves is right here, and we're going to rotate it around the line y equals 1. Now realize that the point at which y equals x and y equals the square root of x intersect at is the point 1, 1. So y equals 1 will be right around here. So we're going to rotate around this line. Now realize that there is space between the axis of rotation and the region itself, so we have to use the washer method because there's going to be a hole in the solid. So once again, I'm just going to write out the formula for the washer method. pi times the integral from a to b of the capital R of x, or the outer radius squared, minus little r of x, or the inner radius squared, times dx. Once again, we are rotating around a horizontal axis, so we have to put everything in terms of x. So rewriting the formula, volume equals pi times the integral. Now for our bounds of integration, obviously there are two intersections, one at the origin and one at 1, 1. So our bounds range, or our x bounds range from 0 to 1. So we have pi times the integral from 0 to 1. Now for our outer radius squared, once again the outer radius is going to be the distance from the axis of rotation to the outer curve. Well, the outer curve in this case is y equals x. But realize in this case we are rotating around something other than just the x or y axis. So every time we rotate around something other than just the x or y axis, we have to take the line minus the curve, and that's going to end up being the radius. So in this case, the line is y equals 1, obviously. So we're going to take 1 minus the curve, and the curve is, we already identified it to be y equals x. So we take 1 minus x, and then that's going to be our radius. We square that. Now same process with the inner radius, or the inner curve. Now the inner radius is going to be the distance from the axis of rotation to the inner curve. This time the inner curve is y equals the square root of x. So because we are rotating around y equals 1, we're going to take the line minus the curve, and that's going to be our radius, or the distance between the axis of rotation and the curve. So 1 minus y equals square root of x is that inner curve. So we have 1 minus the square root of x. And we're going to square that because that's our inner radius squared. And then we do have to finally multiply by dx. So now we can go ahead and just evaluate by foiling on the inside. So we have the volume equals pi times the integral from 0 to 1 of 1 minus x, the entire thing squared. When I FOIL, we get 1 minus 2x plus x squared. And then we have minus, when I FOIL 1 minus the square root of x squared, we have 1 minus 2 times the square root of x, and then plus x, and then times dx. So once again, just a reminder, going back to the formula, every time you rotate around an axis that's other than just the x or y axis, you have to take the line minus the curve and then square it. Now simplifying just what's inside the integral, I'll just rewrite it. We have 1 minus 2x plus x squared. I'll distribute the negative, so negative 1 plus 2 times the square root of x, and then minus x. So then with the 1 and the negative 1 will cancel, and then we have negative 2x minus x, which is going to be negative 3x. So now rewriting the integral, we have pi times the integral from 0 to 1 of x squared. We have plus 2 times the square root of x, and then minus 3x dx. So evaluating the integral, we have pi times the integral of x squared, which is x cubed over 3, or 1/3 x cubed, plus, now I'm going to go ahead and rewrite 2 times the square root of x of 2 times x to the 1/2 power. So I can use the power rule. So the integral of 2x to the 1/2 is going to be 2 times x to the 3/2 divided by 3/2, or multiplied by 2/3. And then we have the integral of negative 3x, which is going to be negative 3 over 2 x squared. And then we can evaluate from the x bounds of 0 to 1. Now just simplifying what's inside the parentheses first, we have 1 over 3, I'm just going to rewrite it as 1 over 3x cubed, plus, now 2 times 2 is 4, so we have 4/3 x to the 3/2, and then we have minus 3/2 times x squared. And then we can evaluate from the x bounds of 0 to 1, so we get pi times, when I plug in 1 for x, we have 1/3 times 1 cubed, which is 1/3, and then plus 4/3 times 1 to the 3/2, which is still 4/3, and then we have minus 3/2 times 1 squared, which is still 3/2. Now minus, when I plug in 0 for x, we just have 0 plus 0 plus 0, so that will end up canceling. So now we have pi times 1/3 plus 4/3 is 5/3, so pi times 5/3 minus 3/2. Now in order to combine the fractions, I can rewrite 5/3 as 10 over 6, and then minus, I can rewrite 3/2 as 9 over 6. So then we have 10 over 6 minus 9 over 6, that's going to be 1 over 6, so 1 over 6 times pi gives us the final answer of pi over 6. Now for number 6, we have x equals y squared, x equals 1, and we're going to rotate the region about x equals 1. So if I go ahead and graph this, now x equals y squared. If I solve for y equals plus or minus the square root of x. We've done this plenty of times in this video. Square root of x is like this. Negative square root of x is the reflection across the x-axis. And then we have the line x equals 1. So the region being created is right here. And we want to rotate this region about x equals 1. Now realize that there is no space between the axis of rotation and the region itself. So we can use the disk method. However, keep in mind we're rotating around a vertical axis. So we have to put everything in terms of y. So the formula for the disk method, once again, volume is going to equal pi times the integral. Now for our bounds of integration, obviously we're using y bounds. And our y bounds, we can guess, obviously it ranges from -1 to 1. But just to double check, we can set the original two equations equal to each other to find that y value of intersection. So if y squared is equal to 1, then y equals plus or minus 1. And that's exactly where those two where those two y values are. So y equals 1. And the bottom y value, or the bottom bound, is y equals -1. So our integral is from -1 to 1, and because we're using just the disk method, all we have to do is take the radius squared. So in this case, the radius is going to be the distance from the axis of rotation to the curve. And in this case, remember that similar to the previous problem, we're not just rotating around the x-axis or the y-axis, we're rotating around x equals 1. So instead of just the outer curve squared, or instead of just the radius squared, we have to take the distance, or the line, minus the radius squared. Now similar to the previous problem, because we are rotating around something other than the x or y axis, we're rotating around x equals 1. For our radius, we have to take the line minus the curve and square it for our radius squared. So the line is x equals 1. So we're going to take 1 minus the curve. Now the curve here, we're going to put it in terms of y, once again because we're rotating around a vertical axis. So we're going to say y squared, 1 minus y squared, that's our curve. Once again, that's our line minus our curve, and then we squared, because that's our radius squared, and then times dy. Now if I go ahead and FOIL what's inside the integral so I can simplify and make it easier to integrate, we have 1 minus y squared squared, which is 1 minus 2y squared, and then plus y to the fourth. So now if I move that down a little bit, I can rewrite it as the integral, or pi times the integral, of 1 minus 2y squared plus y to the fourth times dy, and our bounds of integration stay the same from -1 to 1. So now we have pi times the integral of 1 with respect to y is just y. We have minus the integral of 2y squared, which is -2/3 y cubed. And then we have plus the integral of y to the fourth, y to the fifth over 5. Let's go ahead and evaluate from the bounds, or from the y bounds, of -1 to 1. So we have pi times, when I plug in 1 for y, we have 1 minus 2/3, and then plus 1 over 5. Minus, when I plug in -1 for y, we have -1 minus 2/3 times -1 cubed, which is -1. So that's going to be -2/3 times -1, which is positive 2/3. And then we have plus -1 to the fifth over 5, which is going to be minus 1 over 5. Now if I simplify even further, we have pi times, I'm going to rewrite everything inside, so 1 minus 2/3 plus 1 over 5, and I'm going to distribute the negative into the parentheses. So we have plus 1 minus 2/3, and then positive 1 over 5. So we have pi times, now 1 plus 1 is going to be 2. We have -2/3 minus 2/3 and minus 4/3. And then we have positive 1/5 plus another 1/5, that's plus 2 over 5. So then we have pi times, now common denominator here is going to be 30. So I'll rewrite 2 as 60 over 3, or 60 over 30. Minus, I'll rewrite 4/3 as 40 over 30. And then plus, I'll rewrite 2/5 as 12 over 30. So then we have pi times, now 60 over 30 minus 40 over 30 is going to be 20 over 30. 20 over 30 plus 12 over 30 is going to be 32 over 30. Now 32 over 30 can be simplified into 16 over 15. So our final answer is going to be 16 pi over 15 for the volume of the solid.